In this video, I want to talk to you about a class in the java.math package called Big Decimal. When you use a float or double, the operating system determines how much precision you'll get. For a float, this is usually between 6 or 7 significant digits in the decimal place. For a double, this is usually 16 digits. I want to start back at the basics for just a minute and again review precision and scale. Precision defines the number of digits in a decimal number. Precision includes digits to both the left and the right of the decimal point. Scale is the number of digits to the right of the decimal point in a number. How a number is stored in Java is determined by the type you choose. Precision and scale become especially important when performing math. Let's look at an example in code. I've created a new project called Big Decimal, and I've got my main class open. Imagine that you work for a life insurance company and you're responsible for generating the code to distribute funds to beneficiaries. The last client who recently passed away had a $100 million policy. He has 3 beneficiaries with equal shares. I'll create a local double variable called policy amount and set that to the numeric literal for 100 million. I'm making this a double so that all math will be calculated with doubles. I'll set up my beneficiaries to be 3. I'll get the percentage first as a float by dividing 1.0f, a float literal, by the number of beneficiaries. I'll do the same, but I want to double this time, so I'll just use 1.0. Now, I'll just print out some data. I'm going to take the percentage float and multiply the policy amount by that, and I'll do the same thing with percentage, the double. Running this code. I can see that my 2 payout amounts are different. The expression that used the float is $1 off. It's actually overpaying by $1 for each payout. I'll next print out the differences between my calculation and the policy amount. I'll set up a local variable called total using float. I'll set that to the policy amount minus the payout for each beneficiary, but I'll multiply that by the number of beneficiaries. If the math is right, I should always get 0 here. I'll print that out. Next, I'll copy those last 2 statements and paste that copy just below. I'll call the second variable just total instead of total using float. I'll replace percentage float with percentage on the next line. I'll also replace total using float with total on the line after that. I'll run that. And here you can see clearly that using a float has overpaid the payout to beneficiaries. But even this number feels wrong, doesn't it? If I wrote 3 checks for the payout amount, wouldn't I be $2.99 over and not $2.98 since each payout is $1 over? This happens because there's 1 penny that wasn't included. It couldn't be divided evenly with a 2-digit scale. The stored number has additional values we're not seeing in the decimal part of the number, even though we might have written a check for a 2-digit decimal amount, the 33 cents in other words. Doubles are working, so maybe you think that's good enough. But again, consider we've said each check amount includes 33 cents. Why then don't we have an extra penny laying around somewhere? 33 times 3 is 99 cents. Where's that extra penny? This is caused because we're storing a payout amount without rounding it to 2 decimal places. Obviously, we can't split the penny and add that to each distribution amount, but we could adjust 1 check to include it. This would make the payout amount exactly equal the sum of the distributions. These lost pennies will add up if you do enough transactions with them, so losing or gaining a penny on each transaction isn't acceptable. For this reason, the Big Decimal class is recommended for financial applications. Big Decimal lets you control how numbers are rounded without losing precision in calculations. First, many floating point numbers can only approximate the decimal number they're supposed to represent. Think about the number 1/3, which has an infinitely repeating decimal. This fraction, by necessity, will get rounded at some point. Its scale wasn't big enough as a float when we applied it to our fairly large life insurance benefit. The double worked well enough for this calculation, but it was still off by a penny when reconciling a rounded dollar amount with a calculated double amount. The Big Decimal class stores a floating point number in 2 integer fields. The first field holds an unscaled value with a type of big integer, another class in the java.math package that can store numbers bigger than even long values. The second field is the scale, which can be positive, 0 or negative. A positive or 0 scale defines how many digits in the unscaled value are after the decimal point. You can use a negative scale as well, which means the unscaled value is multiplied by 10 to the power of the negation of the scale. That probably sounds confusing, so I'll show you an example shortly. Using the examples I showed you on the first slide, if I created big decimal instances, using those values I would get the unscaled value and scale shown here. The unscaled value has all the digits and no decimal point. The decimal point's placement is determined by the scale, and again precision identifies the number of digits. I'll go back to my project and set up a little code that will create big decimals for each of these examples. First, I'll set up an array of string and use an array initializer to declare 4 strings that match the numbers I showed you on the slide. Next, I'll set up an array of big decimals and initialize it to the same size as my string array. I'll use arrays.setAll, passing it my big decimal array, and for each I'll create a new big decimal instance using one of the constructors available, which takes a string value. I'll now loop through my big decimal array and print out the unscaled value, the scale, and the precision. I will print this out in a tabular format, so I'll start with a header row. I'll format the headers so the values can be lined up under them. I'll use an enhanced for loop to access each of the big decimals in my array. I'll print a formatted string using negative widths in my specifiers to left align values. I can get the unscaled value, the scale, and the precision using methods on the big decimal class, so I'll include those. If I run this code, I'll get output that looks a bit like the table on my slide. You might be wondering why I set up all my numeric values as strings rather than just an array of doubles. I'll do that next. I'm going to copy the lines, starting with the string array declaration, down to the closing brace of the for loop and paste that directly below. I'll change that string array to an array of double primitives and call that doubles. I'll remove the double quotes around each of my numeric values. I'll remove this big decimal array declaration line, and I'll just use the existing array of big decimal instead. I'll also replace tests with doubles in the big decimal constructor argument, so the big decimal instance is being constructed using a double value, not a string value. I'm also going to insert a separator line in there on line 40 so you can see the new output better. That's all I need to do, so if I run this, look what I get. My values represent the floating point approximations for the double values I specified. For this reason, it's highly recommended that you don't use the big decimal constructor that takes a double. The string constructor is much more precise. Notice that IntelliJ was trying to warn me about this by highlighting that constructor. I'll hover over that, and I can see that this constructor can be unpredictable, as you've just seen. I'll just use IntelliJ's recommendation to replace with big decimal.valueof. This replaces the new big decimal constructor code with big decimal.valueof, passing it my double. If I run this code, I'll get similar output to the previous for loop, but with one exception, the number 8, the double 8. In this case, 8 is represented with a scale of 1, so its unscaled value is 80, and its precision is 2. The value of method converts the double argument passed to it to a string using the double wrappers toString method, and then calls the constructor version that takes a string. This gives more predictable results, but it's not without problems either. Let me show you that next. First, I'll create 2 new instances of big decimal. The first will take a string that has a number with 25 decimal places. The second will use big decimal.valueof with the same numeric value. I'll copy the code starting from the line separator through to the closing brace of the for loop and paste that just after the test2 declaration. I want to first change the widths in the first printf statement for the first 2 cases because this number is large. I'll remove the for loop from around the last printf statement. I'll change 15 to 30 in that printf statement. I'll replace BD with test1 on the line below that in all cases. I'll copy that last statement that spans line 53 and 54 and paste a copy on line 55. I'll change test1 to test2 in all 4 cases on the last line. Okay, so now if I run this, what I want you to see is that when I use a string representation of a number, I'll get that value in the big decimal, exactly as I specified it in the string. This isn't true of the value of method, passing it a double. That's because a double has a scale that's 16 digits long. Because of the limitations of storing floating point numbers as approximations and the limited scale used, you should always use the string constructor to create a big decimal for a predictable value. I'll comment out the code starting at test 1 all the way down to the last printf statement. I'll end this video here on the introduction to big decimal. In the next video, I'll show you how to change the scale on a big decimal instance. Specifically, I'll be using big decimal and its methods to clean up my life insurance example. See you in the next video.